Now let's look at a few standard graphs. Again, these are graphs that you have already studied previously, either in your coordinate geometry, quadratic equations, or any other chapter. We are just going to be revising all those graphs so that it becomes easier for you when you look at the questions of area under the curves. So for example, here you can see the graph of y is equals to x has been given to you. It passes through the origin, and here we have been given the graph of y is equals to mod x. Now I hope you all remember, if anywhere we have a modulus sign, we have, let's say, a function which has been entirely bracketed under modulus, then whatever function used to be below the x-axis simply just goes up. For example, here y is equals to x, you can see that in this portion it is below the x-axis, right? And when we put mod in the x portion or in the entire function, what happens is this same function just becomes a mirror image of itself on the x-axis. So that is how modulus functions are generally represented. Here you can see that this curve here represents y is equals to x, and this curve here represents y is equals to minus x, because whenever we have any negative value of x, it is going to generate a positive value of y. That is why it becomes on the upper part of x-axis. Looking at these curves, again, this curve, if you remember, we had studied in quadratic equation, this is our y is equals to x square curve. A complete symmetric curve about the y-axis. This curve basically shows symmetry about y-axis. And now how are they going to ask questions based on, let's say, a curve which has been given this way? So let's say I have to find out the area of let's say my lower limit is -2 and my upper limit is 0. So again, whenever you have been asked question to find out area under the curve, it is recommended that you draw the diagram first, shade the portion that has been asked in the question, and then find out the integration. So let's say if I was asked from -2 to 0, then how am I going to do it? I would of course mark the portion, I would shade it, and then I would see how I can find out the area of this portion using our integration, of course. So this was our curve, and this curve here, this was also another curve that we studied in quadratic equation. This used to be y is equals to x cube. We also studied details of this curve while we were studying applications of derivatives as well, because there we studied about maxima, minima, and here you can see that there is of course no maxima, no minima. So y is equals to x cube. You must remember all these curves. Let's look at a few more. This one here, this is our y is equals to root x. Again, as we remember the property of anything which is under root, the domain of x which is under root, it has to be greater than 0. That is why we haven't taken any values which is less than 0. So you must remember this thing. Now looking at this curve, this is our y is equals to 1 by x curve. Or in other words, how can I write this curve as xy is equals to 1. And I hope you all remember, we had studied this in hyperbola. Xy is equals to c square. I hope you all remember this. Xy is equals to c square. This used to be a rectangular hyperbola. So that is exactly what is drawn here. Here our c value is 1. So you can see that our vertex for both the curves of this hyperbola becomes 1, 1 and -1, -1. This is basically a rectangular hyperbola which is symmetric about both these axes as well as the origin. So you must remember this as well. Now again, our greatest integer function and our fractional function. So this curve shown here, this is basically our y is equals to bracketed x, which is our fractional function. And I hope you all remember, in our fractional function, y used to be always less than 1 and it used to be greater than equal to 0, because of course our fraction can lie only from 0 to 1. It cannot be 1 or any other integer that we are assuming for. So this is how the graph is represented, and this is our greatest integer function. Y is equals to greatest integer square bracketed x, greatest integer function. And I hope you all remember, here y would always belong to integer category. So this is how greatest integer functions graphs are represented. Of course, it starts from the lower limit, which is included, and it ends up till the lower part of, or let's say it extends up to the upper part, but it is not the upper part. So basically here bracketed x, we can say that this would, here y would always be less than x plus 1, however it would be greater than x, greater than equal to. So what will happen is x value would always be equal to, sorry, y value would always be equal to x. So that is how our greatest integer functions are calculated. It would always be an integer. Now looking at this curve, y is equals to a to the power x, and y is equals to our logarithmic and exponential function. So this is our exponential function, and this is our logarithmic function, and this is how the curves are represented. Of course, both these curves are almost symmetrical about the line y is equals to x, so you must remember this as well. Now instead of, let's say, a, I choose the standard form, which is our e. Y is equals to e to the power x, and y is equals to log ex, or I hope you'll remember we can represent this as ln x. Here the value of e used to be somewhere around 2.7, so this is how the curves are represented. And these again are conic section curves basically that we studied. This is our circle whose equation used to be written in this format: x square plus y square is equals to r square, where r is our radius and our center, since this is our standard form, so our center used to be h comma k or 0 comma 0 in this case. This is our ellipse. Again, there are two types of ellipse. One is our vertical ellipse and the horizontal ellipse. This is our parabola. Of course, the equation of parabola used to be written in this format: y square is equals to 4ax, our standard parabola's equation. And this is our hyperbola: x square upon a square minus y square upon b square is equals to 1. All of these we had studied in conic section. Just a reminder as to how their curves look like, so that it would be easy for you to calculate the area that is bounded under them. Now let's talk about symmetry. Again, nothing much to talk about. Any graph which is symmetric about either a point, either an axis, or either some other, let's say, justified line, so that becomes our symmetry about that point. So if you look at this line here, this is basically our y is equals to minus x, and this line here is symmetric about the y-axis as well as the x-axis. You can see it is symmetric about the origin as well, because it is almost equal on both these sides, right? So it becomes symmetrical. If you look at this curve here is somewhat symmetrical about this point, because the portion that is on the left hand side of this point and the portion that is on the right hand side, they basically look like the mirror image of each other. If you look at this curve here, this is again symmetrical about the origin, the axis, both the axes. This is nothing but our cos x graph. If you look at this curve, again symmetrical. This is our hyperbola curve, rectangular hyperbola. This also seems to be symmetrical. So again, any curve which seems to be equal or seems to be mirror image of either on, it can be on a line, it can be on a point, or any other curve as well. So that becomes our symmetrical graph. Now talking about inequality. I hope you all remember we had studied this in straight line. Whenever, let's take this question here only, for example, y is less than 2x minus 3 has been given here. So that means this is an inequality here. There is not an equality. Had this been an equality, y is equals to 2x minus 3, it would simply had been a straight line. However, since it is an inequality, that means it is not just a straight line, it is an area that is bounded by this curve. So how do we know whether this portion is our area or this portion is our area? So what do? Is we do this by point method. Let us take any point which is on any one of the sides of the axis, of the line, and take another point which is on the other side of the line, and we try to put those points in our equation, and if that point satisfies our equation, that means that portion is our shaded one and the other one is not. So for example, in this graph here, let us take 3 comma 0 for example. Let's see if it satisfies our equation. Y is less than equal to 2x minus 3. If I put this becomes 0 less than 2 3 is 6 minus 3 becomes 3. So basically this is satisfied. So this point basically is satisfied. That means this lies under an inequality. So this entire shaded portion would become our answer. Let's say if I was to take the origin and check whether it is lying in our inequality area or not. So if I take origin for example, and if I put it in the equation, it becomes 0 less than equal to minus 3, which is incorrect. So that means this portion does not satisfy our equation, and the portion which is on the other side becomes our answer. And other way of also looking at this is, you can see that they have given us y is less than 2x minus 3. That means you always have to choose the value which is below this line. So if you look at this line carefully, the value which is below this line, these values of y, this would only be our answer. Let's say if the equation had been y is greater than equal to 2x minus 3, then we would have said that since all these values of y lie above this line, so that would have become our answer. So this is how you shade the portion, or you find out the area bounded by inequalities.